have a little think about different types of quantity in physics. We divide quantities into two kinds in physics. We have quantities which just have a size, and they're called scalars. And we have quantities which have a size and a direction, and we call those vectors. So a scalar is size only, and a vector is size and direction. So let's take a few examples. An obvious example of a scalar would be mass. If you think about mass measured in kilograms, then it doesn't really have a direction. The mass is just the mass. It's not in any particular direction. On the other hand, if we think about weight, which is a force measured in newtons, then it does have a direction. It's a force, gravity is a force acting downwards. So weight would be an example of a vector quantity, and in fact force is an example of a vector as well, because it goes in a particular direction. It could be upwards, downwards, forwards, backwards. Another distinction between scalars and vectors is when we're thinking about movement, and if we had a measure of the speed of an object, then speed would just be a scalar quantity. It just is a number of meters per second. It doesn't have a direction. But velocity is defined in terms of size and direction. So your velocity might be 5 meters per second forwards or 10 meters per second upwards. Velocity, unlike speed, has a direction. Acceleration as well is another commonly used vector quantity which has to have a direction. You can be accelerating forwards, you can be accelerating downwards under gravity. You've got a size and a direction. Now we have a particular way of representing vectors. Very simple notation. We use arrows. So for the weight, for example, you might use a downwards arrow. Force, you could have an arrow in a different direction. Velocity, lots of different directions could be used. But the point about an arrow is it's telling you two things. It's telling you direction and also size. The length of the arrow corresponds to the size of the vector. And one of the things we can do with these arrows, these little vectors, is we can add them up. Suppose, for example, I start off here and I go on a journey which is across a bit, and then I go on another journey which is up a bit. The net effect of that journey plus that journey is the same as just one journey there. Okay? So I can put my arrows together top to tail and I can add them up. And this is important when we're combining forces. Suppose, for example, I have a force that's pushing something downwards and another force which is pushing it sideways. Well, that again is going to be the same as a single force going in that direction. So vector quantities can be added up by putting the vectors top to tail. A simple case of that is where they're in opposite directions. Suppose, for example, I've got a ball which is falling downwards and it's got, let's say, 100 newtons of weight and maybe 5 newtons of drag as it falls downwards. Well, 100 downwards and 5 back upwards leaves me what we call a resultant force of 95 downwards. Okay, so that would be the vector sum of those two forces. 100 downwards minus the 5 upwards gives me an effective resultant force of 95 downwards. So vector quantity is very useful in physics, lots of different cases where we can use them. And remember, the key difference is that vectors have a size and direction, scalars have only